In this video, we will be learning about the chain rule, which is a rule that helps us find the derivative of composite functions. So first of all, as a reminder, composite functions are when you have a function within a function. So for example, f of g of x. And f of g of x can be written like this or like this. G of x is the inside function, f at x is the outside function. So I'm just going to start with a little warm-up, kind of an advanced functions question here. And we're going to find each composite function or each point in the composite function. So I have these four functions, and first thing, f of g of x. So g of x is going to be my inside function. So I always like to write my inside function first and just replace g of x with its equation. And now this just tells me, okay, go into function f and replace x with x plus 2. So instead of the square root of x, the square root of x plus 2. The other way around, g of f at x. First, I'm going to swap in the inside function, so the square root of x. And now I'm replacing x in g of x with root x. So root x plus 2 instead of x plus 2. In the next two, we're going to evaluate actual points on composite functions. So for f of h at 2, I'm just going to work from the inside out. So in the bracket, I'm going to write what h of 2 is. H of x is 3 to the power of x, so I need to write 3 to the power of 2. I'm replacing x with 2 in h of x, and then I'll evaluate that. 3 to the power of 2 is 9. And now, typical function notation, I'm going to go into function f and replace x with 9. And the square root of 9 is 3. So this would represent a point on the composite function. 2, 3 is on f of h of x. I of g at negative 2. So I'm going to start from the inside. G at negative 2 means negative 2 plus 2. Just replacing x with negative 2. That's just 0. And now I at 0, so cos x or cos 0 is equal to 1. Thinking back to the cos function, it starts at a maximum. The maximum is 1. And now two more composite functions, but we have three functions going on here. H of f of g of x. It's going to start from the inside out. So h of f of and g of x is x plus 2. Now I'm going to put x plus 2 into f of x. There it is. Actually, this one we had already done. I could have cleaned that up right away. And now I'm going to replace x with this in h. So instead of 3 to the power of x, we're going to have 3 to the power of x plus 2. And same thing for the last one, starting from the inside. F of x is root x. That's going to go into function h first, so 3 to the power of x, 3 to the power of root x, and then finally into function I, so we're going to do cos of 3 to the power of x. So just refreshing on how to find composite functions, looking at inside versus outside functions. Now, the chain rule, we've already kind of seen the chain rule with the power of a function rule. If I had 2x plus 3 all to the power of 5, the derivative would be bring the 5 down, copy paste the inside, now it's to the power of 4, and then take the derivative of the inside. So that actually was a chain rule. It was just very specific to polynomial functions or functions that just have exponents and the x's are not exponents, so this doesn't work for sinusoidal or exponential functions, but it works when we have numerical integers. So what we did here is we took the derivative of the outside function, which was something to the power of 5, and then we dealt with the inside function after, and that's exactly what the chain rule is. If I have a function f of g of x, its derivative is take the derivative of f first, copy paste g of x, then take the derivative of the inside function. And we can also compare this to the Leibniz notation. If I have an outside function, my outside function is f at u, and the inside function is u, which is g of x. So if we combine these together, f of u is f of g of x. Then the derivative, which with Leibniz notation we would write dy dx, is take the derivative of, oh sorry, that should be a y, not a v. Take the derivative of y in terms of u first, so that's taking the derivative of the outside function, and then take the derivative of u in terms of x, and that's for the inside function here. So, I mean, for the chain rule that we're going to be looking at today, it's going to be pretty much just the power of a function rule, but this is going to be important when we learn how to take the derivative of sinusoidal functions like sine and cos or tan, or when we learn how to find the derivative of exponential functions. So we're going to differentiate each function and then state restrictions if necessary. So my outside function is something to the power of 3 over 2. So we're going to deal with that first. Bring the 3 over 2 down, copy paste the inside function, subtract 1 from the exponent, you have a half. Now we're going to take the derivative of the inside, which is 2x plus 1. There it is. Derivative of the outside, then derivative of the inside. If I wanted to clean this up a little bit, I would really just replace the 1/2 with a square root, so this is kind of it. But if I write this square root instead of the 1/2, then I can see, okay, my restriction is from the square root because I need to have a positive number under the square root. And it's not just a nice linear expression under the square root. So I actually will take this one step forward and I'm going to factor under the square root. And this is helpful because I can draw out my parabola of x times x plus 1, so I can see when that parabola is positive. So the zeros are 0 and -1, and the parabola is opening up. So here it is. So this shows me if I pick a value greater than 0, then x squared plus x will be positive. Or if I pick a value less than -1, I will also be greater than 0. But I can also be equal to 0, so I'm just going to be equal to 0 and -1 as well, because this isn't a fraction. It's not in the denominator, it's up on top, so I can square root 0, no problem. And there we have it. So this should kind of remind you of how we did restrictions for log functions when we had to draw out the parabolas back in advanced functions. All right, next one, g prime of x is equal to, my outside function is something to the power of 5, so I'm going to deal with that first. 5 root x plus 1 to the power of 4, and now I'll take the derivative of that inside. So remembering that this is x to the power of a half, so 1/2 x to the -1/2, and there we are. If I want to clean this up a little bit to see my restriction better, I'll keep the first part in the numerator, the 2 and the root x goes in the denominator. If I wanted to rationalize this, I can multiply top and bottom by root x. Regardless, I can see that my restriction is x has to be greater than 0. For the next two, we're just going to keep them in unsimplified form. So just take that derivative the first step, because these are going to be a little bit more interesting. So for h of x, I have the chain rule because I have something to the power of 4. But then I have a product rule inside as well. And for the next one, I have a chain rule because of the square root, but then I have a quotient rule inside. So it is going to be a longer question. So we're just going to keep it in that first unsimplified form and then write a restriction if one exists. All right, so let's start with h of x. So I'm going to start with the outside function, which is something to the power of 4. So I'm just going to write the 4, copy paste the inside. And now it's to the power of 3. So there was the outside function. Now for the inside function, I have a product rule. So now I have to go switch into product rule mode, which is take the derivative of the first function. So 2x minus 4, copy paste the second function, that's inside, plus take the derivative of the second function, so 8 minus 1/2 x to the negative 1/2, copy paste the original. And there it is. A much longer derivative, but that's because we had rules within rules. And in terms of the restrictions here, I have a square root, so I have to worry about that, and that would go in the denominator. So my restriction is just that x should be greater than 0, not equal to 0. For k of x. So similar idea, but we're going to have the chain rule and then a quotient rule. So bring the 1/2 down, copy paste the inside. Now it's to the power of negative 1/2. And now we'll do a chain rule. So the derivative of the top, copy paste the bottom, minus derivative of the bottom, copy paste the top, all over the bottom squared. And there we have it. And for this one I said no restrictions, because this restriction is a little bit more. All right, there it is. There's our chain rule, quotient rule combo. And now let's go to a very typical derivative questions, finding the equation of a tangent line. So we have f at x, and we're going to find the equation of the tangent line at x equals -2. So for the slope, I need the derivative. So I have a chain rule and a product rule. The product rule is on the outside though. So I'm going to start with the derivative of the first function, and the derivative of the first function is a chain rule. So bring the 2 down, now it's to the power of 1, then the derivative of the inside. So this is all the derivative of the first function. Now I'll copy paste the second, plus derivative of the second function, copy paste the first. Now, normally I might clean this up if I wanted to do more with this, but because I'm just trying to find the slope when x is -2, I can sub in -2 right now. I'm just gonna punch this into my calculator. I can show my work and everything, but I'm just gonna sub it in. And when I sub it -2 in for all of those x's, I do get -1,562. I also need to know what the coordinate is. So here's my slope. The coordinate itself, I'm going into the original f at x, and the coordinate is 1,089. So bigger numbers here. That's okay though. And now let's go into y equals mx plus b. Okay, there's my slope. I'm gonna plug my point in. And clean this up. So, very typical question. Okay, there's my y-intercept, and putting it all together, y equals -1,562x minus 2,035. Okay. The final two really focus on the Leibniz notation for the chain rule. So for the first one, we're going to determine the specified derivative. Y is equal to 2u squared minus 4u. U is equal to 2x cubed, and we have to find the derivative of y in terms of the derivative of x. And this is just showing me, here's my outside function, here's my inside function. And Leibniz notation says, okay, if I want to take the derivative of dy dx, I'm going to take the derivative of y in terms of u first, because that's what we have, and then we'll multiply that by the derivative of u, which is in terms of x. So I'm going to do that first. The derivative of y is going to be 4u minus 4. And the derivative of u is 6x squared. Now obviously we don't want this to be in terms of u and x, but u just represents that inside function. So once I finish, I'll go in and replace u with the inside. So we'll have 4 times 2x cubed minus 4 times 6x squared, which is 8x cubed minus 4 and 6x squared. And I can distribute that if I wanted to take another step with it. But here, the purpose of this notation is it really makes sure that when you're doing your chain rule, you don't take the derivative of the inside right away, because we just copy pasted what the inside was. The inside is u, and that's what we did. For the next one, we have x is equal to 7z minus 4, and y is equal to 3x to the power 5, and we want to find the derivative of y in terms of z. So here our outside function is y, and the inside is x. And that's because x is in terms of z, and there's no equation of z in terms of something else. So the y has to be our outside. Plus, it's asking us for dy dz, meaning I need to take the derivative of y in terms of x first, which is the equation I have, and x in terms of z, which is the combo I have as well. So the derivative of y would just be 15x to the 4, and that's going to get multiplied by the derivative of x, which is just 7, and now we can bring the actual x in, and the reason I have to do that is because it's asking us for the derivative of y in terms of z, and I don't have z's here, I have x, so let's put this back in. And there we have it. And I could multiply the 15 and the 7 just to clean it up a little bit, because I'm definitely not going to expand something to the power of 4. Perfect. And final one, given h of x is equal to f of g of x, f of u is the parabola, g of negative 2 is negative 1, g prime of negative 2 is 3. Let's find h prime of negative 2. So first of all, we don't actually know what g of x is. But something I can conclude, because it's f of g of x, I can conclude that u is g of x. Okay, so if I'm taking the derivative of h of x, it's going to be the derivative of the outside function, so the derivative of function f, and then we would be copy pasting g of x, but g of x is just u, and then we're going to multiply that by the derivative of u. Okay, and now let's actually do that. Okay, so here I was just kind of replacing g of x with u and applying that chain rule. So the derivative of f prime is 6u plus 4, and that would get multiplied by whatever u prime is. And unfortunately, we don't know what function u is. I mean, we know it's g of x, but I don't know what g of x is, so I can't actually take its derivative. But that's okay. Our end goal isn't to figure out what h prime of x is, it's to figure out what h prime of specifically negative 2 is. So I'm going to do one more step before I bring in the negative 2, which is I'm going to make things in terms of g, because that's the information I have here. So h prime of x is going to equal 6 times g of x plus 4, and then times g prime of x. So now that I have this, now I'm going to replace all of my x's with negative 2, because that's the goal. And lucky for us, we know what these values are. G of negative 2 is negative 1. G prime of negative 2 is 3. So I'll just sub those values in and clean it up. So 6 times negative 1 plus 4 times 3. So that's negative 6 plus 4, which is negative 2 times 3 is negative 6. So even though we didn't know what u or g of x was actually equal to, because we had a little bit of information about g at negative 2 and g prime at negative 2, we were able to find the derivative of this composite function at negative 2. And that's it for chain rule. Like I said, at this point in time, the chain rule is pretty much identical to the power of a function rule that we've already learned. But keep in mind this idea of take the derivative of the outside, copy paste the inside, then the derivative of the inside, specifically when we get to trig and exponential derivatives.